Hi, thanks for tuning in to this short lecture on routing history, the historical background of the modern internet. My name is Professor J Patterson. The internet that we have today derives from a history of networking technologies that have come before, each one progressively getting more complex and adding new capabilities to the network that we know today. The future of our modern internet includes a pretty radical transformation that's going to include low Earth orbit satellites, part of the network. The path to a resource, meaning the path from some origin computer to some destination computer, can vary. And usually you don't need to think very much about it. And the path that your data takes from one location to another is independent of the scheme that you choose to use. For example, HTTP, HTTPS, SSH. So let's start with digital communication from the beginning. Early on, the telegraph is probably the earliest example of digital communication between 2 points. Communication happened by a code called Morse code. It was originally introduced by operators who would tap a button in a particular pattern, and then operators at the other end that would listen to that pattern and would translate dots, short dots and long dots into letters so that simple communication could be sent from one location to another. In some cases, these communications were rigged to be sent over the barbed wire that went around large fences, and eventually they were able to be sent across country over transmission wires. Now, they were always carried over, they were initially carried over physical wires, and it was only possible to send them from point to point. So if you wanted to send a message from one location, maybe on the East Coast of the United States, to another location on the West Coast of the United States, occasionally the message would have to be collected by points in between and then forwarded to other operators in other places. So say, for example, you were sending a message from New York City to Los Angeles. It may have to travel from New York to Chicago, from Chicago to Kansas, Kansas to Colorado, Colorado to San Francisco, and San Francisco to Los Angeles. Maybe. Each one of those hypothetical peering points would be connected by a single physical wire. And at the end of those physical wires was a human operator who would have to listen for the message and then retransmit the message down the next leg of the physical wire. Possibly the first thing to be considered digital communication. Eventually, this process was expanded so that Morse code did not need to be sent on the wires, but instead people could communicate by voice over these wires. And instead of having an individual that would listen to the voice message that the message that you were communicating by voice and passing that on to someone else who would pass it on to someone else, much like the kids' game telephone, circuit switched networks were set up. You may be familiar with old images of operators that were working at switchboards. They were creating circuit switched networks. What they would do is they would sit at pairing points and they would physically connect one origin to one destination, causing there to be a single wire, a single electrical connection that routed, say from our hypothetical example of New York, all the way down to Los Angeles. Instead of having human operators listen to the Morse code and then transmit it down the next line, a human operator would listen for where the caller wanted to call to and would set up a circuit to the next transmission point, at which point another technician would connect the message, say from Chicago to San Francisco. They would create a physical connection along the way, taking some time to build up a connection, and once the connection was built, the person at the origin could speak to the person at the destination. This was called circuit switching. Physical connections had to be made between endpoints. Because of these physical connections, there was limited scaling. It wasn't necessarily possible for everyone who wanted to make a long-distance phone call to make a long-distance phone call at the same time, because there were only so many opportunities for these physical connections to be made. Now, eventually, there were multiple routes that could be made between two different endpoints. You might want to route a communication from New York south first and then to the West Coast, or maybe all the way across to Seattle and then down the coast. Multiple opportunities means that at each one of those peering points, there was a choice about how to send information. Eventually, this was able to be automated. Packet switching was the network that brought this automated switching process to the foreground. And what happened was a digital message would be constructed at one end, it would be chopped up into a lot of different pieces, and it would be forwarded automatically along the wire. At the peering point, the destination of those packages would be evaluated, and it would be sent automatically down a wire to the destination, possibly different routes. And at the destination, all the chopped up little pieces would be reassembled into the original message. You could imagine maybe a voice message being sent this way, a recorded voice message. Maybe it would be chopped up into 5-second increments, and each increment could be sent down different routes and then reassembled. The main reason why this packet switching network was built up was to withstand a nuclear attack. It was designed by the Defense Advanced Research Project Agency, and it was the origins of our current internet. Let's look at what this might look like. Let's say at an original location you had a file, and we're going to represent that file in 3 chunks, a blue, an orange, and a green. Your computer would like to communicate that from the left side to a computer on the right side. And so with the destination in mind, each one of those packets would be wrapped up in something like an envelope with a return address and a destination address, and would be sent out into the network. Each one of the nodes along the way would decide what would be the best next node to send this packet to on the way to its ultimate destination. So for example, in this particular set of chunks, we might forward those chunks in this way. And as they travel along the network, they may encounter traffic, and they may encounter nodes that make different decisions for different packets, because of course the packets aren't all coming from one location. They're coming from many locations and going to many other locations. So in this example, green travels down and orange travels up. And you'll see that actually, because of this slow speed, orange, the middle package, actually arrives first. And the destination computer waits for the rest of the packets to arrive. When all the packets have arrived, the destination computer reforms the original file and passes it on to the application that's waiting for it. This is the way that most communication happens on the internet now over TCP/IP. Bits of files are chopped up and sent onto the network, and the remote computer reassembles them. If any of the packets get lost in translation, for example, not in translation, in transmission, then the remote computer says, hey, I'm missing one of the packets, please resend it, and the origin computer will attempt again to resend the missing packet. What's good about this? Well, one of the things that it's very good for is it allows multiple computers to use the same wires at the same time. So physical operators who had to make a circuit switch connection could only make that connection for one origin and destination pair. But in a packet switch network, many different organizations can communicate over the same wire by chopping up the communication into little bits and shuffling them in between and handling them as they come. This, like I said, provides resiliency against network outages. If one particular computer in the middle of the internet should go down, well, the packets can be rerouted in a different path to get to their destination. This also allows traffic control. If there's a lot of communication between 2 endpoints, maybe a Netflix server and an urban environment, different kinds of routes could be established on demand as traffic comes and goes, rises and falls. This process also is agnostic to the physical media. So while in my diagram I demonstrated the packets being transferred over what looks like physical wires, those packets could also be traveling over wireless networks, or a combination of wired and wireless networks. It could even be transmitted over a variety of different styles of networks. One could be an audio transmission, or it could be transmitted over ham radio. There's a variety of different ways in which it is possible to split up the network. Although most of the time it's carried over physical media in fiber optic or electromagnetic wires. One huge change that we're going to see in the next few years is a change to the way the internet works. And we're going to see the introduction of low Earth orbit networks. One that is particularly well known is Starlink, a low Earth orbit internet provider that is coming online recently. They're not the only ones, though. Several companies are rushing to create new low Earth orbit networks. These are called LEO networks. These are constellations of many hundreds and in some cases thousands of satellites that move around the sky, and they're not geosynchronous. So from the perspective of the ground, if you were to look up and see one of these, you would see it traveling across the sky. It wouldn't be in a fixed location. And these satellites act as nodes in the network that would collect packets and forward them on to another node in an effort to get it to its destination. But what's different about this particular kind of network is that while in our classic model of the internet, each one of the intermediate nodes is stationary. It may go down, it may disappear, it may come back, but when it is present, it is in one location. These low Earth orbit networks, however, are going to have intermediate nodes whose position is changing over time, and in some cases quite rapidly from the perspective of a human anyway. So those routes from an origin to a destination are going to be changing very frequently and very often as satellites fly by and get closer and farther apart to one another, or as satellites go over the horizon and are no longer visible from a client's perspective. What this is going to be very good for is it's going to allow our origin and destinations, where we're sending packets to and where we're sending packets from, to be located all over the globe. This is going to provide global coverage without geographic access. That's a really interesting idea, because what it means is that you'll be able to have digital communications without having wires on the ground, or without having transmission towers for wireless networking points. It means that you no longer have to have geographic control in order to have an internet that's present. These networks are high speed and low latency because they're at low Earth orbits. You may be familiar with medium Earth orbit satellites, geosynchronous orbit satellites, or high altitude orbits as well. These orbits are higher and take much longer to transmit information. It's appropriate for things like broadcast TV, where the majority of the conversation, or the majority of the transmission, is one direction. So what does this kind of look like? Well, here's an artist's conception of what such a network might look like. It kind of looks like a big net in the sky if you imagine the connections between satellites as being lines. But remember that all of these networks are moving, and they're not moving in conjunction with one another. They're moving somewhat chaotically around the planet. And so they're constantly having to reconfigure the route to get from one location to another. And so in this case, you see a green line representing different transmissions from origins to destinations. Strategically, this is going to be a real change. One thing that it will support is it will support remote data centers. So you could imagine that there would be kind of a data center in a shipping container, something that's been prototyped by Microsoft, for example. This data center might be powered by renewable resources like solar or wind that's located on the container. The container itself can communicate to the internet using a low Earth orbit network. And internally, there might be several computers that are processing information, collecting information, or redistributing information, all from a containerized data center. Of course, this is also going to support global military action, because again, digital communication will be possible without having control of the ground. It will also support applications for the developing world and rural applications. For example, you may live in a location that's somewhat rural and not have a lot of access to internet service providers. And those that you do have access to charge a very high fee for very low bandwidth connections. This is going to change that dynamic. Rural areas will now have high-speed connections, much like their urban counterparts. On the other hand, it's not clear that urban centers are going to be able to effectively use low Earth orbit satellites as well. Because of the congestion in urban areas, there's likely going to be a lot of communication overlap with co-located clients and servers in urban centers. The ability for the low Earth orbit satellite providers to mitigate this congestion remains to be seen. Just a rough history, a little bit of a timeline so you can put these different developments in order in your head. It's roughly around the 1840 timeframe that electrical telegraphs took off in the United States. About 1898 was the advent of widespread telephone switchboards, for example, the one that was installed in the US Capitol building. And around 1970, packet switching and TCP/IP were invented to connect predominantly military and university computers across the United States. And then it was 2019 when the Starlink low Earth orbit network began to become operational, not in a commercial setting, but in a testing and beta testing scenario. And certainly this is something that's going to become more prevalent in the near future. So our key points. The internet of today derives from a history of networking technologies. And if you understand the background of our networking technologies, it helps to explain how we got to where we are today with our packet-switched, dynamic, resilient networks. The future of the internet is going to include a radical new change in low Earth orbit satellite networks. But the path that your particular communication takes from an origin computer to a remote computer may vary. And it may vary by going through landlines or orbital connections. It might travel through wires or wireless connections. And for the most part, the internet takes care of this heterogeneity, and you as a client don't have to think much about it. The path that your data takes from one place to another is independent of the scheme that you are using, whether that's TCP/IP, UDP at the low level, or HTTP, HTTPS, or some other scheme at a higher level. I hope this gives you a little bit more appreciation for the resiliency that's built into the modern internet and the way in which it promotes free and unrestricted communications around the globe, both for good uses and for bad. Thank you for your attention.